We're in Rosen, Discrete Mathematics and its Applications, section 13.5 on Turing machines. And here we're going to talk about two different applications of Turing machines. One is to recognize sets and the other is to act as a function. When recognizing sets, what we consider is V, which is a subset of our input alphabet I, input and output alphabet I. And then here we consider X, in this case, to be a string. Earlier we had considered X to be a symbol, but this is a string of symbols in V star, and recall that V star is the Kleene closure of the set V. It's all possible strings using the symbols in V. And then we say that it recognizes a string in V star if and only if T, starting in the initial position, with X on the tape, halts in a final state. And I have to define what a final state is. That is a state which does not appear as an input to any 5-tuple in F. Remember, F is a partial function from the set of states and inputs to states, inputs, and direction. And if you have a state which does not appear as an input, then the machine halts in that state, we say that it is halted in a final state. And then we say that a Turing machine recognizes subset A of V star whenever X is recognized by T, if and only if X belongs in A. So it recognizes everything in A, then we've got a Turing machine that recognizes A. Now we can use the other symbols not in V to accomplish this recognition. I can have more symbols than V. And we will notice that these are extra symbols that are used as markers to make sure we're reading the string properly, whether it is unto recognition or non-recognition if it shouldn't be recognized. So, and if we're looking at X on our tape and we halt in a non-final state, or we don't halt at all, then we have not recognized that particular string. You might recall from section 13.4 that there is no finite state automaton that recognizes the set 0 to the n, 1 to the n. But we're going to see that we can construct a Turing machine that recognizes it. To do this, we'll have our vocabulary to be 0, 1, but our input and output alphabet to our Turing machine will have the required blank symbol, but we'll also have an additional symbol, M, which will be our marker. We do have a final state, meaning that will not appear as the input state for any 5-tuple. And then we'll see that our Turing machine starts with the leftmost 0, and we'll replace it with an M, and then we'll go to the rightmost 1 and replace it with an M, and we'll sweep back and forth, terminating in a final state if and only if the string consists of a block of zeros followed by the same number of ones. Here is the Turing machine that accomplishes this recognition task. And if we started with the string 3 zeros and 3 ones, it would successfully become these sequence of strings here with each external 0 and 1 replaced by an M until we replace them all with M's and the machine halts in the final state. And I will leave it to the student to actually run through all of the steps that the Turing machine goes through to replace these zeros and ones with M's and halt in that final state. And then the student should also attempt to try to run strings that do not get recognized to see how the machine handles different inputs that should not be recognized. And be 1, 1, 1. Okay, that's recognition. Let's talk about computing functions with Turing machines. So we said that Turing machines are the most general model of computing. Well, computers do recognition, but computers also compute functions. So let's do that with this Turing machine. If we want to have input as x and it halts with a string y on its tape, we can say that the Turing machine returns y on input x. And And if we want to have multiple inputs, we could say that we could input a k-tuple into the machine. So that would be more than one number input. And then for simplicity, we use what's called the unary representation of integers. The way we do that is we have n plus 1 ones represent the number n. So 0 is represented by a single one, 5 is represented by 6 ones, etc. And then if we want to input a k-tuple into our Turing machine, we will need to have some kind of separator. So to input the 4-tuple 2, 0, 1, 3, I would have a unary 2 separating with an asterisk, and a unary 0 separated with an asterisk, a unary 1 separated with an asterisk, and a unary 3 on my tape. And this is, it can be frustrating to build these types of machines, but our interest in this is more theoretical rather than practical. And I'll give a hint as to how difficult writing down Turing machine functions can be in just a bit. Let's compute a rather simple one next. I want to construct a machine that adds two numbers, n1 plus n2. That means I have to input a 2-tuple, which will be n plus 1 ones, followed by an asterisk, followed by n plus 2 ones. The machine starts at the leftmost one and erases it. If the next character is an asterisk, that means I was adding 0 to a 1. Then all I need to do is replace that asterisk with a blank and halt. Otherwise, we want to erase that 1 and then pass over all the remaining ones till it comes to an asterisk, then replace that asterisk with a 1. All right, so here's the 5 tuples that define this machine. And so the student should verify what happens with various different functions. If I want to add 1 and 2, what does that look like? If I want to add 0 and 4, what does it look like to add 5 and 1 with my Turing machine? And as an indication of how complicated these can be, if I want to create a Turing machine that multiplies two numbers, it has 31 5-tuples and 11 states, at least a commonly known one does. So again, these are more of theoretical interest, but the student should understand how they work. And that is the use of Turing machines to do recognition and to compute functions.